Welcome everyone to lesson 7 on chemistry. Today we are going to be looking at hybridization. So first off, with hybridization, it really goes into what we talked about last time with our SPDF orbitals and sublevels. But firstly, I think it's important that we should study this little thing called valence bond theory. So I just have an example here that I want to go through first. So there's this one famous compound called of C6H6 or benzene. It's one of my personal favorites as it's a pretty cool structure. It's over here on the right. But from an outside view, we just see, okay, there's a carbon that has a double bond with another carbon, a single bond with another carbon, and a single bond with the hydrogen, right? And that's pretty much going around the ring of like every carbon has that, right? Well, if you actually look at it, these little bonds and stuff, like where you would expect like an electron to be here, electron, 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 that's really just areas of probability because we study that orbitals aren't designated locations of where electrons are, rather they're just areas in space of where there's a high probability of finding an electron. So that's where we get into this model here. So I just kind of drew this up in which we kind of can see that these little regions that we have highlighted here, right? So we have blue, then we have green, yellow, red, or orange, and then red. These kind of just represent the different densities of electrons. So in this case, we have our red, which is a high electron density, and then all the way going out with the rainbow to our blue, which is a low electron density, which correlates to here. Because if we look at this diagram right here, right, we'll have an electron here, 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 and here in theory. But then as we go out, right, hydrogen has less electrons than this carbon right here. So this model is important to look at because it really just ties in our studies with Lewis structures to our studies with orbitals. Because it just reminds us that even though we draw Lewis structures as being little lines and little dots and stuff, those dots really don't exist. There's just a huge area in which those dots can be found. And that's why it's important that we can understand this. So these are kind of what I like to call electron clouds. So these electron clouds can be constructed for a particular atom to represent the areas of high electron probability, like we did here with electron density. So what the valence bond theory really states is that atomic orbitals will overlap in order to form new orbitals with a pair of opposite spin electrons. Because when we have a bond here, right, it's really just this orbital and this orbital kind of forming together, right? So these orbitals, like from the name, are kind of a hybrid between the orbitals from two other atoms. So I'm just going to call valence bond theory VBT. So we'll just define it down here that VBT is the theory stating that atomic orbitals overlap, forming new orbitals with a pair of opposite spin electrons. Yeah, I'm just using E minus for electron. Okay, so we're just going to look at a quick second example. So I'll just get rid of this, pause it if you need it, but Okay, so our example here is going to be looking at a hydrogen or two hydrogen atoms. So we have two hydrogen atoms. Okay, so as we know, hydrogen is the first element. So when we look at its electron configuration, it's just 1s. So we have 1s, and then if we remember with the Hund's rule and how we draw electrons, we just use the up arrows and the down arrow for plus 1/2, minus 1/2 spin. So this is pretty much our orbital box diagram for hydrogen, right? So the electrons reside in 1s. And if we have two hydrogen atoms, then we have a second hydrogen atom with its own orbital box diagram over here, right? Well, when the two separate 1s orbitals overlap, right? Because if we have two hydrogen atoms coming together, like because if you remember, hydrogen's Hofbrinkel, so it's typically found as being H2 gas, right? So there's the two. So let's just say we have these two kind of overlapping. Then a covalent bond forms, right? It would, just to refresh, an ionic bond is a transfer of electrons, but a covalent bond is when we have like an electrons here, and we have two atoms kind of sharing the electrons. So the electrons that are bonded in the 1s orbital then get an opposite spin. So what happens here is, in the first stage, we have two separate atoms, right? In the second stage, these separate atoms kind of get different charges. So let's say we have one here. I'm going to use circles now instead. So we have one like this, and then this one on the right we can represent like this. Because if we have two plus 1/2 charges, it won't cancel out, right? It won't. We need a positive 1/2 and a minus 1/2 in each orbital box, as we remember from the previous lessons. So then we have these two separate H atoms, or hydrogen atoms. And then our third step is going to show the overlap. So once they overlap, we're going to have this one. I'm just drawing them bigger just for reference, but they don't actually increase in size. We have the first one and second one, just like this, and just like this. And then lastly, they form a covalent bond. And it looks something like this. So pretty much any unfilled orbital, like we have here with the two 1s's, right? Because they're both unfilled, they can overlap with any other unfilled orbital. So for our second example here, we're going to be looking at hydrochloric acid, or HCl. So basically, HCl is formed in the reaction between hydrogen gas and chloride gas, or chlorine gas, to make HCl, right? Well, if we look at it through the eyes of SPDF orbitals and everything we've kind of been talking about, we have the molecule, right? HCl, which also has covalent bonds, right? The hydrogen atom contributes one electron from its 1s orbital to form the bond. Because if you remember from just before, hydrogen is really just 1s, right? But chlorine, right, if we're going to draw its orbital box diagram, is a lot bigger. We have, I'm just going to ignore the one and the two, like the first and the second energy level. I'm just going to skip to the third. We have 3s, and we have 2 here, and then we have 3p, 1, 2, 3. Remember to follow Hund's rule, so 4, 5. And then after that, we would have a 3d orbital, and then we would have 1, 2, 3, 4. So this one isn't filled, but we just need it for this demonstration right now. So we'd have a 3d orbital here. So here, the 3s orbital and two of the 3p orbitals are full with electrons with opposite spins. This one, and this one. Well, this one is just only half full, right? So this 1s from the hydrogen atom will overlap with this Cl. Because if we remember from just before, the valence bond theory states that atomic orbitals will, just like these two, will overlap to form a new orbital. So what's basically going to happen is the p orbital in Cl, right, this one right here, it has two lobes, right? If we think back to like our SPDF with S being kind of like this, P kind of looking like with their two lobes, and the D was more complicated, right? So the p orbital in chlorine has two lobes, and when the bonds form, there's one chlorine lobe that overlaps with the one S from the H. So if we go back to our valence bond theory, we have our hydrogen, and then we have our chlorine, which is a P. So we go like this, and then we have one like this, and then this is chlorine, this is hydrogen, and they form this funky shape. So it goes like this, and then we have this kind of bond together between the H and then the Cl. So we can see that this Cl, which was upwards, facing upwards, it, using valence bond theory, changed to being a downward spin in order for the two of them to bond together. So now we have an upward spin and a downward spin at this side of the bond. So it's the overlap of the 1s and the 3p. So they're kind of overlapping. I'll just draw little arrows here. And then after that, we are left with hydrogen chloride, which looks like this. HCl, right? Hydrochloric acid. If we think back to the VSEPR theory from SCH3U, the VSEPR theory assumes that the majority of electron density for bonded pairs of electrons is in the vicinity of the bond. So things get a little bit more complicated when we use polyatomic valence bond theory, where we have two or more, potentially, atoms combining. So we're just going to consider the following. So consider NH3, ammonia. So this shape, if we can think back to our VSEPR, it's trigonal planar. Trigonal planar. So nitrogen, its orbital box diagram looks like this. I'm just going to, again, ignore the first energy level. So we have 1s, and then our 2s is going to be here. And then we're going to add in our hydrogen orbital box diagrams. So we'll just, as we were doing before, just have our 1s. So now we can kind of just draw the interactions. So we're going to be starting with our nitrogen. So I'm going to draw in our nitrogen. It's going to start with our p orbitals. Remember, these are like two lobes for each one. So we'll just go like this. Maybe it's kind of like figure eights. It's kind of pretty when you look at it, right? And we have, I'll just use downwards arrows now just to show how we have the hydrogens with up arrows, just for simplicity. It doesn't really matter which one's up or down, just as long as you know that they're going to be opposites. So we'll use an N in the middle here for nitrogen, hydrogen, hydrogen, hydrogen. So these are all going to interact, right? We're going to have the p orbitals interacting with the s orbitals from the hydrogen. So once that happens, we're going to have some overlaps. Then we're going to have this. I'm going to do my best to draw this. It's going to be a bit tricky. So most of our orbitals stay the same, but then some of them are now going to have more electrons on them. So now we can draw in our hydrogens, and they're kind of just sticking like little magnets like we had in our previous example. And we have our same charges here, but now we have the positive spins from the hydrogens. And we have hydrogen here, hydrogen, hydrogen, and then our central nitrogen. And then now, this is kind of just showing how this is like our overlap between the two. And then after that, we will soon have 3 covalent bonds, and they will look like this. So same lobes, kinda. I'm gonna redo this, sorry. And then we will have 1, 2, 1, 2, 1, and 2. And then we'll have just nitrogen here as the central atom. And this is basically what our ammonia is going to look like, right? NH3. So rather than using our Lewis structures, so the sticks for our bonds and the little dots for our electrons, this takes into account that we don't really know where the electrons are. So instead of representing an electron kind of sticking out like this, we represent it as this cloud of uncertainty, right? So it's far more accurate into what electrons really are and where they really are. So with hybridization, it's also very important that we can express it using more ways than just drawing our simple Vesper shapes as we just did. So we're going to try examining valence bond theory, right? But this time through the eyes of orbital box diagrams. So let's just give an example. So we'll say example 1 is going to be methane. So methane is CH4, right? 1 carbon and 4 hydrogens. So let's just see what we have here. So when we have carbon is 1s2, 2s2, p2, right? So if we were to draw that out in orbital boxes, we would have, again, I'm just going to ignore the first energy level and skip to the second one because it's the one that's important in this case. So here we have the 2s and then the 2p. So we have 1, 2, 3, 4. And then we have our hydrogens, so we have 4 of our 1s with 1. There we go. So basically, when we place these four electrons, right, these 4 valence electrons on carbon, one of the 2 electrons in the 2s orbital wants to go to the empty 2p orbital. Since the s and the p orbitals have a different shape, they're going to form 2 types of chemical bonds with the 4 hydrogen atoms. So what's going to happen here is we're going to have these p orbitals and these s orbitals, and they're going to kind of combine because we have carbon, right? And in this case, we're really just saying carbon's like this, with a hydrogen, 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 hydrogen. Carbon needs 4 spaces in which it doesn't have an electron, or it needs 4 orbital boxes in which it only has 1 electron, right? Because if we were to imagine this, if we were to remove these hydrogens, we really just have carbon with a 1, 2, 3, 4 electrons that are ready to be paired with something else, right? Another way that we can represent that is by having, let's say we have 4 orbital boxes, and we have 1, 2, 3, 4 unpaired electrons, right? Well, we're going to kind of take advantage of that, and we're going to create hybrid orbitals. So hybrid, right, being in the name, we're going to kind of combine 2 of them. So we're going to combine our 2s and our 2p orbitals. So in this case, carbon is attached to, it has 4 bonds, like I said. So what's going to happen is we're going to have one of these s orbitals and then 3 of these p orbitals. And then we're just going to kind of have it like this. I'm just going to do this for now. We're going to write 2s. We're going to write them next to each other for a sec. We're going to go boom, boom, and this is our 2p, right? So we basically have these 2 orbitals combined together, right? We're just adding them. But another way that we can write this is by getting rid of this and seeing, okay, what sublevels do we have? Well, we have an s and a p, right? So we know that it's going to compose of s and a p. How many s orbitals does it have? Well, it only has 1, as this one. So we're going to leave that as s to the 1, right? So because it only has 1. So we don't really need to write a 1 there, right? It's kind of just implied. But how many p orbitals do we have? Well, in a p block, there's 3. How many did we use? 3. So this shape is not going to be called 2p or 2s, it's going to be called sp3. Right? Again, we can have like the 1 in here if we really want to see that 1 and 3 add up to 4 with 1, 2, 3, 4. But basically it's letting us know that we have this new hybrid shell of orbitals, which is going to fill up like this: 1, 2, 3, 4, using 2 electrons from this and 2 electrons from this, right? It's like in a 1-to-1 ratio. And now we have this new sp3 hybridized orbital. And then once these 4 hydrogens come in, right, we have our little like 1s over here, right? We have our another one, and then another one. And they're going to approach, and when they bond, it's going to go boom, 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 boom. Now we're just going to have a full shell, right? That's how methane is formed. But it's important to note that in this case, each of these sp3 orbitals has the same shape. Now you might be wondering, okay, what's the shape? Because we went into this in an earlier lesson. We had our s orbitals, which is like a sphere. We had our p orbitals, which were like these 2 lobes, right? What's sp3? Well, this is where we get into some new shapes. So if you can think of balloons, right? Imagine you have balloons tied together in a string, right? Or like tied together by their bases, right? Because if you see a balloon, right, typically it'll have like its little like hole here connected to a string. But just imagine we have a bunch of balloons all connected by this piece. So how many balloons do we have in this case? Well, how many orbital boxes do we have? 1, 2, 3, 4. So let's just hypothetically imagine connecting 4 balloons all by their ends. So you go 1, 2, 3, and then we'll have like 1 in the back. Right? Well, this is what a tetrahedral looks like. We have our carbon in the middle, and we have our hydrogen, hydrogen, and hydrogen. And this is basically what it looks like. So this shape is called tetrahedral. So tetrahedral correlates with sp3. And remember, these shapes are really just locations in which you're very high at finding electrons. And we're just going to go through some more examples though to kind of teach a few more of the shapes. But just keep that in your mind that really when we're going to imagine the shapes, right? Because I know you have your VESPR knowledge from previous years. But when we imagine the shapes for hybrid orbitals, we really just want to instill that all of these lobes in which you could find electrons in space are kind of just like balloons when you put them all together. So our second example is going to be looking at beryllium hydride. So we have BeH2. Now beryllium is the 4th element on the periodic table, so its electron configuration is 1s2, 2s2, right? And then we can ignore the 1s, and we can just look at the 2s. So here we have a 2s orbital, and it's filled. But then past that, although we haven't used it yet, we still do have a hypothetical 2p orbital, right? It's unfilled, but if we had any more electrons, they would go into here, right? So now what we have though is we have these hydrogens that are coming in, right? Just like last time, we have a hydrogen here and a hydrogen here, right? 1s and 1s, and they want to bond. So let's just look at this though. Let's say we have these 2 hydrogens that are approaching. What are they going to bond with here? We have a full shell and we have a bunch of empty shells. They're not going to want to enter just like these random empty shells, right? Have a 2p orbital. No, they're going to hybridize. So basically, what's going to happen here is there's going to be a promotion, is what it's called. So promotion for the 2s. So basically, we're going to have one of these electrons, right? And one of these electrons is going to say, okay, well, we need a space for 2 electrons from these hydrogen atoms, right? So that means that we need 2 of these orbital boxes that are half full, right? So we can fill them up. So we have 2 electrons here, right? And we're going to split these 2 electrons into their own individual valence electrons. One of them is going to be over here, as this is the 2s, and then through the promotion, we had a second one right here, which is the 2p. And again, we can rewrite this and say, how many s orbitals do we have? 1. How many p orbitals do we have? 2. This is called the sp shape. Not sp3, not sp2, just sp. 1 s and 1 p. And then if we take these electrons, we can disperse them, going 1 and 2. And this is our new hybridized orbital. So then when these hydrogens come in, and they say, we want a bond, then where are they going to go? Right here, making our bond. And what this kind of looks like is we have beryllium here, and we have a lobe going out like this, and a lobe going out like this. These would connect, but I'm just using the beryllium to show it here. And then we have a hydrogen, and then a hydrogen. And this shape is linear, right? Not tetrahedral, linear. And it is sp. So it's really important to just take home that when we're naming them, we want to just count how many orbital boxes we have. So just looking back on it, we have sp, and sp is linear, and sp has an initially a s orbital like we had before we had to promote it to a p orbital, and then it kind of just looks like this. And then although we didn't do an example on it, sp2 is pretty self-explanatory. This is trigonal planar, just your old Vesper shapes. And this is initially 2s and 2p, and its shape is like this, this, and this. Just imagine if you have balloons, how are they going to react? Well, they're all going to kind of, if we can imagine like a flat surface here, they're all going to kind of sit like this, with one sticking out like that, right? And that's kind of just like a side view of what we have here. So this is our trigonal planar sp2, and then our sp3, which we saw in our first example with methane, is going to be tetrahedral. It's going to consist 2s and 2p again, and its shape is going to look like this. Just again with those balloons. So yeah, one little thing that's important to note that I'll write down here is that the number of atomic orbitals that mix equals the number of hybrid orbitals that form. We can see that here because we have our sp, which is just an s block, right? It's just initially that, and we take an s block and then part of a p block, so that's just 2, right? And then we have our trigonal planar. We have an s and 2 from a p. That's going to be 3. So we have 3 atomic orbitals making a hybrid that's going to be 3 orbitals big. And then our sp3 tetrahedral is we're going to take the s and the entire p block, and we're going to make 4. So we have 4 atomic orbitals initially, 3 in the p, 1 in the s, and we're going to have 4 sp3 orbitals. For our third example, we're going to be looking at water. So we have water, H2O, and water is always going to be our bent shape, looking like this, our bent polar molecule, right? This is our Lewis structure. This is kind of how we know it. So we have our 2 hydrogens, which are going to be, like always, 1s and then 1s, half filled, and then we're going to have our oxygen, which is going to be 2s and then 2p, and then we're going to go like this, there. So this is oxygen, and then these are the hydrogens, and like respectively. So what's going to be happening here? Well, let's take a look at it through the Lewis structures. We're going to have our oxygen. Let's take a quicker, like a more in-depth peek at oxygen. So oxygen, when it bonds, it's going to be, ignoring the hydrogens here, it's going to have 2 electrons here, 2 electrons here, right? We can see that. But then with this hydrogen, it's only going to have 1 here and 1 here, right? Because the other one is going to be provided by the hydrogen and the hydrogen to make 8. But before you complete the octet though, there's only 6. so we see here and we say, okay, well, how many bonds are kind of being formed about oxygen, or how many regions around the oxygen atom are going to consist of electrons? Well, we have this region right here, which has 1 electron, right? And we have this region right here, which has 1 electron. This region has 2. So does this one. We haven't really seen this before, right? We can kind of see with the regions. So we think, okay, how many regions are there that are important throughout water when it's bonded with hydrogen? Well, there's 4. 2 of them have 1 electron, and 2 of them have 2 electrons. So if we say, okay, we need 4 regions, let's think. We have an s orbital and a p orbital. 1 of these and 3 of these, how many would that make? 4. Oh my gosh, let's do that. So let's combine these, hybridize them, and instead of making 2s and 2p, let's make sp3. And then now we have to use Hund's rule again and say, how many electrons do we have in these? We have 1, 2, 3, 4, 5, 6. So we have 6 electrons to fill up. So let's just use Hund's rule, 1, 2, 3, 4, 5, 6. Right? Well, this actually aligns perfectly with our oxygen here. Because if you look at all of our, if you imagine this little region here as its own orbital, it has 2 electrons. Well, this orbital has 2 electrons. Let's go to this one. 2 electrons, 2 electrons. But then 1 electron, 1 electron, 1 electron, 1 electron. So this is the hybridized shape that oxygen takes when it produces water. This is the hybridized oxygen atom. So when these waters come in, and they bond with it, we have another tetrahedral shape. So it's going to look like this again, with our lobes, right? And then we're going to have I'm going to draw the hydrogens down here. We're going to have a hydrogen and a hydrogen. We're going to have our central oxygen, which I'll label with red. That's an O. And then we're going to have, though, 2 electrons here and 2 electrons here. Or if we want to draw it more appropriately, upward spin, downward spin, upward spin, downward spin. Showing that these orbitals are complete. They have 2 electrons already. They have an upward spin and a downward spin. There's an upward spin here and like a downward spin here, upward spin and downward spin, which is why we need the hydrogens. But the other ones, they can just rest on their own and they're perfectly fine. So this is our tetrahedral shape for water, or oxygen hybridized to make water.